In the gigantic universe where mysteries multiply and the genuine surface of spacetime is stretched out quite far, a huge mystery has emerged. How we could decipher the improvement of the universe is at an intersection with new proof, testing deep-rooted speculations and suggesting hidden-away powers that could reshape the genuine preparations of cosmology. Join us on a trip through the latest disclosures and significant jumps into the secrets of the universe as we examine the hypnotizing and questionable question. How fast is the universe genuinely developing? Something is off with how we could decipher the universe. Cosmology is apparently making a beeline for a confrontation over maybe its most focal question. How fast is the universe stretching out? For more than 10 years, two sets of measures have been in battle. View of the universe today for the most part shows that the speed of augmentation, known as the Hubble constant, is around 9% speedier than assumptions. Considering information from the early universe, experts trust that the James Webb Space Telescope, the most advanced telescope ever built, would help settle the question unequivocally. Yet as of now, no arrangement has been shown up at. Rather, the Space Observatory has developed the uniqueness with incredibly careful pivotal discernments that did whatever it may take to overturn the standard model of cosmology. The new physical science expected to rethink or try and replace this 40-year-old speculation is now the topic of discussion. One captivating and enchanting possibility is that there is something we don't grasp about the universe. Join us as we explore the new, truly significant pictures from James Webb that have recently certified that there is something really amiss with how we could decipher the universe. Our universe started with an impact, the Big Bang. Energy, mass, and space showed up in a passing second. Then, the young universe formed a murmuring, developing plasma of matter and antimatter particles that appear to obliterate each other on contact. Left to their own devices, the matter and antimatter inside this plasma should have tanked each other. Yet specialists accept that a dark disproportion allowed more matter than antimatter to be made, subsequently saving the plasma universe from immediate collapse. Gravity squeezed pockets of plasma, compacting and warming the material so that sound waves going at around a portion of the speed of light, called baryonic acoustic oscillations, undulated across their surfaces. Meanwhile, the high energy density of the early universe and its expanding things stretched spacetime, pulling a little piece of that matter out of the contention. As the universe expanded like an inflatable, the standard story goes that normal matter, collaborating with light, joined around imperceptible lots of dark matter to shape the vital universes, connected together by a colossal grandiose web. At first, as the things in the universe expanded, its energy density and consequently its speed of augmentation decreased. However, around a long time back, the universe started to advance at a continuously increasing rate. The explanation was a new, undetectable, and confusing component called dark energy. The most uncomplicated and most notable explanation of dark energy is that a cosmological constant, an inflationary energy, is the same everywhere and always woven into the texture of spacetime. Einstein named it lambda in his general theory of relativity. As the universe has broadened, its general matter density has reduced, while the dark energy density has remained the same, constantly making dark energy the biggest supporter of its general extension. Taken together, the energy densities of common matter, dark energy, and light energy put forth an upper line on the speed of the universe's extension. They are also key parts in the cosmological lambda cold dark matter, lambda CDM, model, which directs the universe's creation and predicts its end, with matter eventually extending until it will encounter a stage known as the Big Freeze. Some of the model's predictions have proven surprisingly accurate. However, this is where the issues start. Regardless of much research, cosmologists still don't know what dark matter or dark energy is. As Ofer Lahav, professor of cosmology at University College London, who studies dark energy in galaxies, puts it, most concur that the current design of the universe is 5% ordinary baryonic matter, 25% cold dark matter, and 70% dark energy. The humiliating truth is that we don't comprehend the last two yet. A much greater danger to the lambda CDM model has emerged. Relying on the methods astrophysicists use, the universe appears to be expanding at different rates, a disparity known as the Hubble tension. Preliminary data of the early universe show that it was extending a lot quicker than lambda CDM expected. These methods have been checked and confirmed by various observations. As astrophysicist Adam Rice, Nobel laureate and head of the team that made James Webb's new measurement, said, "The only explanation I can see right now for why they differ is that the model we have between them might be missing something. Measuring the expansion of the universe requires more than radar." The primary method to measure this expansion looked at the so-called cosmic microwave background, CMB, a remnant of the first light in the universe made only 380,000 years after the Big Bang. This leftover is visible almost everywhere in the sky and was measured by the European Space Agency's Planck satellite to find the Hubble constant with an error of under 1% from 2009 to 2013. In the Planck picture, the universe is totally homogeneous, yet the hotter and colder regions where matter is more or less dense reveal places where the baryonic acoustic vibrations have made it bunch together as the universe extended outward. This web structure evolved into an infinite web, a complex network of fibers along the convergences of galaxies. By studying these waves with the Planck satellite, cosmologists have calculated the amounts of ordinary and dark matter, as well as the value of the cosmological constant or dark energy. Combining these into the standard model gives a Hubble constant of around 67 kilometers per second per megaparsec. Let's focus on that number for a moment. If a galaxy is 1 megaparsec away from us, that means it is retreating from us and we from it at a speed of 67 kilometers per second. At 20 megaparsecs, this pace of recession reaches 1,340 kilometers per second and continues to increase. Assuming a galaxy is more than 4,175 megaparsecs away, it is retreating from us faster than the speed of light. A second method for finding this expansion rate uses pulsating stars called Cepheid variables, dying stars whose outer layers of helium grow and contract as they absorb and emit radiation, causing them to occasionally flicker like distant beacons. In 1912, astronomer Henrietta Swan-Leavitt discovered that the brighter a Cepheid star, the slower it flickers, allowing cosmologists to check a star's absolute brightness and hence gauge its distance. It was a milestone discovery that made Cepheid variables the omnipresent standard candles for measuring the vast size of the universe. By combining observations of Cepheid variables, cosmologists can build measurements of immense distances, with each step taking them further back in time. It is perhaps the most reliable method astronomers use today to measure distances and build a cosmic distance ladder. Space experts first build the ladder by selecting nearby Cepheids and measuring their distances against light. Wendy Friedman, an astrophysicist at the University of Chicago, explained that the subsequent steps use only Cepheid variables. Next, cosmologists looked at the distances of the stars and supernovae on each bar and compared the degree of the redshift of their light, which shifts toward longer red wavelengths as the universe expands. This allowed for an exact measurement of the Hubble constant. In 2019, recent teams used this method to focus on the Hubble Space Telescope at one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their results were strikingly high, showing an expansion rate of 74 kilometers per second per megaparsec compared to Planck's measurement. However, Hubble lacked the precision needed for the chaotic regions of space the team was studying, causing some of the distant Cepheids to blend with nearby stars. Critics have argued that this striking result could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve this discrepancy or confirm it. The 6.5-meter wide Webb's mirror is almost 3 times bigger than Hubble's, which is just 2.4 meters wide. Furthermore, James Webb can detect objects nearly 10 times fainter than Hubble and is also much more sensitive in the infrared range, allowing it to see across a broader spectrum of frequencies. By comparing the Cepheids measured by James Webb and the galaxy NGC 4258 with bright-type IA supernovae, another type of standard candle, since they all explode with the same absolute brightness, Rice and his colleagues produced a nearly identical result of 73 kilometers per second per megaparsec. Different measurements, including one made by Friedman with the Hubble Space Telescope of the fast-fading type IA supernova and another of light bent by gravity from massive galaxies, returned values of 69.6 and 66.6 kilometers per second per megaparsec, respectively. Another result using light bending also gave a value of 73 kilometers per second per megaparsec. Cosmologists were puzzled by these outcomes. Ronan Kai, a cosmologist at the University of California, said that the temperature of the CMB is measured to 1% accuracy and the distance size of the Cepheids is surely known. The discrepancy in the Hubble constant measurements has led to profound questions about our understanding of the universe. This tension between different measurement methods and their resulting values poses a significant challenge for cosmologists. It indicates that our current models may be missing crucial elements or that we might need to revisit our assumptions about the universe's expansion dynamics. One intriguing avenue of investigation involves the nature of dark energy. While it is commonly associated with the cosmological constant introduced by Einstein, dark energy might not be as straightforward as initially thought. Researchers are exploring various theories that could potentially reconcile the differing measurements of the universe's expansion rate. For example, alternative models propose that dark energy might evolve over time or vary across different regions of the universe, which could influence the expansion rate in ways not accounted for by the current lambda-CDM model. In addition to dark energy, scientists are also considering modifications to the laws of gravity. Some theories suggest that general relativity, which has been the cornerstone of our understanding of gravity for over a century, might not fully capture the complexities of cosmic expansion. Modified gravity theories, such as those involving additional dimensions or alternative gravitational models, are being examined to see if they can account for the discrepancies in the expansion rate measurements. Another significant factor in this ongoing investigation is the role of neutrinos. These elusive particles, which are known to interact very weakly with other matter, could have an impact on the expansion rate of the universe. Recent studies have suggested that the mass of neutrinos might be higher than previously estimated. If this is the case, it could influence the rate of cosmic expansion and contribute to the observed tension in Hubble constant measurements. Cosmologists are also delving into the effects of early universe conditions on the expansion rate. The period immediately following the Big Bang, known as cosmic inflation, was characterized by rapid expansion that could have left lasting imprints on the universe's large-scale structure. Understanding how these early conditions have influenced the development of the cosmos might provide insights into the current expansion rate and its apparent anomalies. The interplay between observations from different astronomical facilities and theoretical models is crucial in addressing these issues. For instance, the European Space Agency's upcoming Euclid mission and NASA's planned Wide-Field Infrared Survey Telescope, WFIRST, are expected to contribute valuable data that could help resolve the Hubble tension. These missions aim to map the large-scale structure of the universe with unprecedented precision, offering new insights into the distribution of dark matter, dark energy, and other cosmic components. In addition to new observational data, theoretical advancements play a key role in this research. Collaborative efforts between theorists and observational astronomers are essential to develop comprehensive models that can account for the discrepancies in the Hubble constant measurements. This interdisciplinary approach is likely to lead to breakthroughs in our understanding of the universe's expansion and its underlying mechanisms. The implications of resolving the Hubble tension extend beyond cosmology. If the discrepancies in the Hubble constant measurements are confirmed, it could lead to revisions in our understanding of fundamental aspects of the universe, such as its age, size, and overall dynamics. This, in turn, could impact other areas of physics and astronomy, influencing our knowledge of the fundamental forces and particles that govern the cosmos. Public interest in these developments is also notable, as advancements in cosmology often capture the imagination of people worldwide. The quest to understand the universe's expansion rate and the nature of dark energy and dark matter highlights the human drive to explore the unknown and seek answers to profound questions about our existence and the cosmos. As researchers continue to investigate the Hubble tension and related issues, the field of cosmology remains dynamic and evolving. Each new discovery, whether confirming existing theories or challenging established models, contributes to a deeper understanding of the universe and our place within it. The pursuit of knowledge in this domain not only advances scientific progress but also inspires future generations to explore the mysteries of the cosmos and push the boundaries of human understanding. In summary, the ongoing debate over the Hubble constant and the factors influencing the universe's expansion rate represents a critical and exciting area of research in cosmology. The combination of new observational data, theoretical innovations, and collaborative efforts among scientists from various disciplines is key to unraveling the complexities of the universe's growth. Whether the resolution comes through refining existing models or developing new ones, This endeavor promises to enhance our comprehension of the cosmos and its fundamental properties, shaping the future of astrophysics and our understanding of the universe.